Yes. Okay. So, first thing we have is electrical charge. Where does that even come from?
The proton and electron.
Ah. What's a proton? Yeah, we're going kind of back to the atoms for a minute. Because we need to talk about electrical charge. And an electrical charge is a property of matter, meaning different materials have different electrical charges. Some materials like to hold on to their electrons really tight, like they just won't let go. Right? Does that make sense? But some materials will take their electrons and they will let some of them go. Okay? And that kind of goes back to when we talked about ions. What's the charge of a proton? Okay. What about a neutron? Neutral. No charge. Okay. What about an electron?
Negative.
Okay. And remember how we had elements that weren't happy? And some of them that weren't happy, they would give their electrons away. And some of them would take. That's where this comes from. Where are your notes? Where everybody should have their notes in front of them. Hayden, everybody should have their notes in front of them. And some things I could be saying you might need. I mean, if you don't know something or you feel like you need to remember it, then you need to jot it down somewhere. That's how this goes, guys. And it's January and y'all have been doing this for however many months. You should know that by now. Okay, so we have a new SI unit. A new SI unit. Yay, I know. Coulombs. Say it.
Coulombs.
Okay. It's a capital C. We will not be calculating anything with it. Yay. But I do want to talk about it for a second. So a proton has, it's like 1.6 times 10 to the 18th, I think. Yeah, something like that. Or maybe 10 to the 8th, I don't remember. 1.6 times 10 to the 18th.
How do you remember that?
I don't know. Positive charge. An electron has 1.6 times 10 to the 18th negative. Okay? So follow me here. Think about how big we said a proton was and how big we said an electron was. And they have the same amount of charge, but one is just negative and one is, but the number's the same. Yeah, but don't you think it's kind of weird that if the electron is so much, like, I think the proton's like 1,800 times, or like, think about how much bigger the proton is than the electron. How in the heck can they give the same amount, but just, I don't know the answer. I'm just saying, whenever I was doing this research, I found it kind of crazy that the electron is so much smaller than the proton, but yet they have the same amount of coulombs, just opposite charge of coulombs. That's weird. I'm sorry, that's weird. Well, the mass of an electron is almost 0. Remember, 0 AMU? And the mass of a proton is 1 AMU. How can they give off the same number of coulombs? No, their mass is, we know that their mass is bigger. It's just weird. It's just like, how does that happen? Yeah, that's very weird. Okay. A charge is what causes a force. What's a force? A push or a pull. So these charges cause a push to happen or a pull to happen. They cause electrical force. Now let me tell you about this. You have gravitational force, electrical force, and magnetic force. All of those, they call them non-contact. What does that mean? Those forces are there and you don't have to touch. See, a regular force, like if I put a force on you, I'm going to have to push you or pull you. That doesn't have to happen for the push or the pull. There can be no contact for the push or the pull. How weird is that? Yeah, you could, but you don't have to. Okay? So these are non-contact. You don't have to have that. They will put the force no matter what. Okay? Out of the three, gravity, electrical, magnetic, gravity's the weakest. That is crazy. Gravity's what holds the whole, like, solar system together. How is it the weakest? Is that crazy? That's crazy. Out of the three, gravity's the weakest. That means electrical force is stronger than gravitational force. I think electrical. I gotta look that back up though. They asked me that today. That's what he just asked. I gotta look it back up. I don't remember. Okay, so we've already decided we have two types, a plus and a minus. The last thing, most important right here. This is the biggest deal. Opposite charges can be isolated. Basically, just charges can be isolated. What that means is I can have just a positive and just a negative. Okay? Why is that a big deal? This is like one of the only things that makes electricity different from magnetism. We're gonna see a lot of stuff very, very similar between electrical charge and force and magnetic. Well, that's what they're saying. I could have just a proton with a field and just an electron with a field. Well, I don't know. Okay? But in a magnet, I can never have just the positive side of the magnet and just the negative side of the magnet. It doesn't matter what you do. You can break the magnet down into tiniest little pieces and you still have a positive and a negative in one. So that's the main difference. In an electric, the charge can be isolated. Magnetic cannot. You will always have a positive and a negative side to a magnet. Nope. Okay. An electric field. Don't make this complicated. I've got a charged particle, and there is space around it called an electric field. Okay? It's not, we don't see it, but it's a space around it. Huh? It's not a theory. No, this is true. There's a gravitational field, there's an electric field, there's a magnetic field. It's just the area where the force is felt. Does that make sense? The field is the area where the force is felt. It says it applies a force to another charged object. Okay? And the objects do not have to touch for that to be there. So it's like, here's my little particle, and around it, there is this area that, in that area, it will apply a force. It's an electric force right now that we're talking about. Okay? Okay, so let's look at the protons. Boom. That is the electric field of a proton. Watch. Watch how it moves. See how it moves with it? As it moves, huh? It's pretty cool, huh?
Yes.
Okay, so look. Okay, hang on. Let me talk about the arrows for a second. So, how do we represent this field? Like, if you can't see it, what do you... Well, it's not that we don't know what it looks like, but how would you draw it if it's just a little space around it? You get what I'm saying? So they use what they call field lines. Okay, that's these arrow thingies. That's the field lines around the charge. Okay? So, let me show you another picture of it. Oh, I didn't open it. Hang on. Oh, wait, it's right here. Okay, this is the electric field for a positive charge. Okay? Watch the negative. What's the difference?
The positive is going out and the negative is going in.
Okay, what that means is the force goes from the positive to the negative. It always moves positive to negative. No, this is just the chart. It goes from the positive side to the negative side. Okay, so you need these two drawings right here, separate. They go underneath your electric field drawing. So look at. I'll show you my notes. No, you should. If you didn't have, you were supposed to have space. Okay, here's mine. That's what yours is supposed to look like in your notes. Positive on one side, negative on the other. Okay? They're on the board too. Up there. Okay, you don't have to draw this picture. We're just going to talk about it in a second. no charge. The difference between these lines is C is the strongest. No, we're still explaining what do these lines mean. What do these lines tell us? They tell us the direction the force is going to be, and they tell us how much force is going to be there. The more lines you have, look, these lines are all closer together, the stronger the force. So C is strongest, A is weakest. And I know that because there are more lines here and they're closer together. You would feel the force greater on C than you would on A. So underneath your little charge drawings, you put in parentheses, if the lines are close, the force is greater. If the lines are close, the force is greater. Okay, so where do electric forces come from? The electric field. The electric field has the forces. Okay, now let's talk about these forces. What's a force? A push or a pull. Okay, so if I take my little positive particle here and I put a negative in there, what's going to happen? Attract? Okay, I said if I'm going to put a negative in there, what's going to happen? They're going to attract. Okay, is the attract going to be a push or a pull? Very good. Y'all are like the first group to get that right. Thank God. So, yes, and it's common sense. So next to attract in your notes, put pull. And what is going to happen if they repel? Push. Yes. So look, just next to this in parentheses, put pull, push. Pull, attract will pull, repel will push. Okay, and we're about to draw this. I'm going to show it to you. Y'all ready? Look at it. You see it? Like, looking if I move it.
Why does it go black? Oh, is that like the field around it?
That's the field, yeah.
Put it beside it.
Put like right on top of it.
So there's no field around it when
Yeah, the field's still there.
when they're right on top of each other?
Yeah. It's very weird, huh?
Yes.
Especially if you put it like
Okay, so look. We're still going positive to negative. Do you see it? Okay. I drew mine like that up there. That, you better label it attraction. That's what that is. Attraction, that goes under electrical force. Electric force, that's the first picture under electric force. These other pictures I got, they look kind of weird. I don't like them as much. Look, you see these? Yeah. These, you can't see it. You can't see it as good. I'm about to. What do you think's going to happen? Up another positive?
I mean,
I'm going to add a positive.
now what about
like charges.
Yeah, that was. What's happening? I was talking about can you do one positive, two positives,
Okay, that right there, that looks.
Pretty cool?
do they ever hit each other?
No. Okay, this is what's happening in this picture. Look how mine is over there too. I don't know what happened to it. I got out of it and it's not showing it the same way. Maybe because I'm not big enough. Hang on. I don't know why. It won't show the lines like it did this morning. Let me try to move it down. I'll show you the sensor. This guy right here, he's saying, get away from me. No, I'm serious. Look, watch. Watch. That's what the sensor shows you. And then this guy right here is telling him, no, you get away from me. Yeah, the closer I go, the closer I go to him, the more force there is. So, it's the same thing.
Oh, they're going head on.
Huh? No, I took it off. Which one? The red one? Oh, yeah, because you know what's happening right there? That's like space. It's like they're... You know how when you take the magnet and you try to like...
Push it together. It doesn't work.
Yeah, it's that space. Yeah. It's like, yeah. It's like they push so much, it's just... And that's why I drew mine that way. So you can see the one on the right is saying, get. And the other one is pushing the opposite way. They don't want to be by each other at all. If you do negative, no, they're like
I feel like the arrows have lit up more.
like, isn't that he's pulling that way and he's pulling that way?
So like the line in the middle of the separator.
Yeah.
So why aren't they going that way though? Like right there. Go back in the middle real quick. When the middle line is going straight down.
That's where I think he's not great.
Right there. Why are
Yes.
See? Look. See that?
That's what nothing is.
Yeah, there's no... See?
Wait, how far does it go to go right on top? Oh,
Yeah, they're stronger. They're stronger. That's the next thing that we're about to do. Okay? If you go look in the book, and I'm going to put the book on here so that I have somebody who's going to be asking today. If you... That wasn't mine.
I don't have one.
I'll take care of it in a second. Okay. 681. $681.
What is that?
Two things determine our amount of force. 681. Two things. No. Number one, the amount of charges. On this side right here, they're saying, okay, the brush only has 4 positives. Well, then 4 positives are only going to be attracted to 4 negatives, so not much hair goes up. In this one, they're like, okay, now I have like double the charges. Well, look at double the hair that goes up. So the more charge I have, the more force I have. That's what Coulomb's law says. Okay? This one, the distance doesn't change. I'm just having more charges. Okay? In this picture, they're talking about distance. It's the same amount of charges on both, but when I'm further away, I have less force. The closer I am, I have more force. So those are the two different ways that your strength of force will change. That was the next thing in your notes. I'm not going to make y'all draw them because it's like, duh. If it's closer, isn't it going to be attracted stronger? Okay, that's what this means. Okay? Now, let's go to the next page. Right there. You can see out the corner. No, it's a balloon. I drew the balloon touching whatever object. This is what goes underneath touching in your notes. You see it? Okay. Actually, yeah, okay, this is right. The amount of charges kind of does matter. So this is my object. Let's say this is my shirt. And then I have, if you don't know, this is a balloon. It's okay. I know I'm not an artist. I said I'm not an artist. Never claimed to be. When they touch, the shirt will lose its electrons to the balloon. So I drew the arrows to show that now I have 1, 2, 3, 4, 5, 6 electrons over here, and there's only 2 on the shirt. I mean, the book picture went to the extreme. Look at all the negatives that the book took. Look at that. That's what would happen. The balloon takes the electrons, picks them up. Yeah, take them. Yeah, he is. He's taking the electrons. He's not going to take the protons. The exchange happens between the electrons. That's why it's called electric charges. Does anybody have any questions about that? No. Okay. The next one is this. Not touching. Okay. So, take the balloon, you put it by a can. The balloon's electrons are going to push all of the electrons in the can to one side. Because what would like charges do? Repel. They're not touching. They're not touching. We're gonna do this. It's cool. We can make the can roll without touching it. Wait, say it again. Because, okay, that's a good question. Because what's going to happen is the positives are going to be right here. The positives of the can are going to end up being more over here. So, because those positives are going to be attracted to his negatives. But since they're not going to come in contact, nothing can transfer. So what's going to happen is they're going to repel. No, the negatives are going to repel, and they're going to put all of the negatives to one side of the can. Okay, now, if I put another can next to it, they'll jump and they'll go that far.
So when you make them, so they roll this way or roll that way?
Because you're gonna have, like, it can't hold that if it doesn't have. You're still okay. There's something called the law of conservation of charge. I'm not going to test y'all on it, but charges cannot be created nor destroyed. The amount that you start with is the amount that you end with. They just get transferred. So he's just going to move some to the side, and he may not have room to move all of those. Yes, when the balloon goes away, they will as long as the Coke cans stay connected, they'll transfer back and even themselves out. That's another process they call electron conduction.
Like, would it make a difference if there's like something in the can, like water or something like that?
No, it's not going to matter what's in the can because this is with the electrons of the can. The aluminum is still the conductor, no matter what's inside of it. The whole way around that. So what if you had aluminum foil around food or something? Is it still not going to let it would still do it? Yes.
You touch the back can while doing it so that it shock you?
You could get shocked if there's a net, it's called a net potential difference between your hand and the can. If your hand and the can have an equal amount, then you don't get shocked. But if there's a potential difference, they're not equal. This is how shock. Yeah, we're going to talk electric discharge. Electric discharge is shock. It depends on what the other one has. Right? My brain just went. Yeah, it just died. I thought it still depends on what the other one has. But I might be wrong. I don't know. My brain just died when you said that. My brain does not. He is fighting me so bad to learn this. He hates electricity and every time I've had to learn this, my brain's like, no. Don't do it. You're not doing it. So how I know as much as I do, I'm not really sure. I might just be speaking a whole lot of just not true. Yeah. I don't know. Read the book and figure it out. Anybody else have a question? If not, I'm done. Yeah, you could add more cans.